Okay, welcome back. Now that we've covered the NVMe over Fabrics overview, and we saw that the NVMe over Fiber Channel, or FCNVMe, actually has pretty minimal configuration requirements on the ESX server side. As for NVMe over RDMA, that's a few more steps. In fact, we can see the outline here. There's, at a high level, there are about 8 major things that we have to do. For instance, on the ESX host, we'll have to install a network adapter that supports RDMA, right? So it's a network adapter, just any old Ethernet adapter, but it needs to be able to formulate RDMA sized or typed frames, right? And this happens to need to be RDMA over converged Ethernet version 2, as most normally known as Rocky version 2. So that needs to be placed in place on your ESX server. Then on the vSphere client, verify the RDMA adapter has been discovered by your host. So you'll find that it actually shows up as its own separate category on the vSphere client. So you have your physical NICs, but you also have the discovered RDMA adapters. You'll then configure your VM kernel binding for the RDMA adapter so that there is going to need to be a VM kernel port, needs to be bound to that adapter, and then verify the configuration for the RDMA adapter. Then enable the software NVMe over RDMA. So that's like creating a software initiated iSCSI adapter. You'll just create it through that wizard. In fact, you just don't choose software initiated iSCSI, and this time you'll install or select software NVMe adapter. Then it will discover the NVMe controllers on your array. You can have it set to automatic or manual. Basically, it's over the Ethernet network, so it can be set to do the whole rescan for the adapters, and then create your data stores on those devices. So let's just take a look at some of those steps. For instance, you've got the RDMA adapter installed. When the server then discovers it, it'll show up as an RDMA adapter. So really what it is, though, it is a physical NIC, right? It's actually a physical NIC that's going to show as 2 devices. It will show up as a physical adapter, and it will show up as an RDMA adapter. And it tells you, in fact, that it is using, or it is VMNIC1, and it's being represented on your host as RDMA or VMRDMA 0. Which also, by the way, will be mapped to a VM kernel port with an IP address so that we're ready to use this adapter specifically through VMK1. Now we need to create the software storage adapter for software NVMe over RDMA. So that's what you'll have to do is you add a software adapter, which is typically the same place that you would add a software iSCSI adapter, but this time we'll choose add a software NVMe over RDMA adapter. Choose the RDMA device that we've just added to the system. So it will choose that adapter, and then you can then fill out the rest under the traditional storage adapters. What it's going to do is it's going to create HBA64, unless that's already taken, and because it's a software adapter, and then you have all the rest of the configuration for the devices and perform a rescan so that you'll see the different NVMe namespaces, and you can go ahead and create a data store on one of those devices. Now, one thing about the NVMe over Fabrics, right, for Fiber Channel and for RDMA, this device will use a different multipathing utility. Instead of using the built-in multipathing plugin, like we usually find with most storage devices, it will instead use the high performance plugin instead. So you may be familiar with the way how vSphere has set up the whole multipathing environment in vSphere. There's what we call a pluggable storage architecture. And the pluggable storage architecture simply means that there is a built-in multipathing configuration for all supported arrays. However, you have the ability to make custom or install custom components. For instance, in the native multipathing plugin, right? The native multipathing plugin is going to be made up of 2 main types of software components. There is what we call the storage array type plugins. These are for the main drivers to communicate with the proper and supported arrays out there. There is an SATP for active arrays. There's an SATP for active passive arrays, and there's an and there's a storage array type plugin for local devices. So, but you may need to add an additional one for maybe some third-party type of storage. So third-party storage may need to have an alternative storage array type plugin installed. It will probably also need its own custom path selection plugin, a PSP. the path selection plugins are basically the ways in which we handle the multipathing on the core storage array type plugins. So for instance, an active array will use typically a path selection plugin that's fixed, or might be using round robin, depending on what the SATP is, right? The other SATP for, say, active passive arrays, they may use a path selection plugin for MRU. All right, so the path selection plugins are the actual multipathing utilities. Then you can install third-party path selection plugins too. So the pluggable architecture allows third-party vendors to add their own custom SATPs. Basically, those are the drivers. And the third parties can also add their own multipathing utilities. However, the third-party storage vendors may also choose to just replace the entire multipathing plugin completely. That's a third-party multipathing plugin where they've already got everything, their entire suite of storage array type plugins and path selection plugins, where they may instead just replace one path selection plugin, or they might need to replace an SATP. The built-in native multipathing plugin has that flexibility that you can add individual components, or you can just replace the entire thing. And that's where NVMe comes in, because NVMe on Fabrics has a whole completely different multipathing plugin called the high performance plugin, which then has its own built-in mechanisms for multipathing and failover and all that. So the high performance plugin for NVMe is the default plugin for NVMe over Fabric targets for both fiber channel and over RDMA. It only supports active-active and implicit asymmetrical unit ALUA or targets, right? So it's either active-passive with ALUA or active-active altogether, and improves the performance of ultra-fast flash devices. Basically, the thing is the native multipathing plugin may not be able to achieve the performance that the NVMe multi-queuing capabilities can offer. That's where the high-performance plugin has really come into play. And in fact, you can enable the high-performance plugin on a local NVMe as well. However, a local NVMe does not use the high performance plugin by default, but for the NVMe over Fabric, it does. So speaking of which, the high performance plugin improves the performance of NVMe devices. Now, for local NVMe PCIe, it's not the default, but it is available. It is really meant and is the default for shared NVMe over Fabric types of storage, both active-active as well as ALUA targets. It provides multipathing, obviously. It also offers like a round-robin latency option like we do with traditional storage. And it also provides its own path selection scheme. It does not provide SCSI-3 persistent reservations, so that's one thing just to be mindful of. And it also does not support 4K native devices with software emulation. And it also does not support vSAN, right? This is if you happen to have a local NVMe device that you've used the high performance plugin on, that isn't going to work with vSAN. vSAN does require you to use the native multipathing plugin on a local NVMe device. So high performance plugin best practices: use that HPP for NVMe local or network devices unless you're using vSAN. Do not activate the high performance plugin for magnetic hard drives or slower flash devices. That's going to have bad performance, right? You only want those high performance plugin just for NVMe types of storage. So when using FC NVMe, use the general recommendations for fiber channel storage. And when using NVMe over Fabrics, don't mix transport types to access the same namespace, right? So we don't want to have some NVMe device in an array that is being accessed over fiber channel and at the same time being accessed over RDMA. That is not supported. Before registering your NVMe over Fabric namespaces, ensure that the active paths are presented to the hosts. I mean, that's a pretty obvious thing. And configure your VMs to use the VMware paravirtual controllers. We want you to use the PV-SCSI controller to provide for the greatest amount of paravirtualized access to these devices, getting high performance for those guests. Make sure your VMs are actually set to high latency sensitivity. That gives them a 100% reservation for memory and can be set for CPU too. That means that the VMs are going to have high performance storage and won't have anything put into a queue or in any paging memory configuration. And if a single VM drives a significant share of the device's I/O workload, certainly consider spreading the I/O across multiple virtual disks. You can attach those disks to separate virtual controllers in the VM, because the VM does have the ability to have multiple SCSI controllers. That was a view of the enhancements using NVMe and configuring NVMe specifically over RDMA using Rocky. And we were able to describe the enhancements of the pluggable storage architecture and the purpose of the high performance plugin. So that ends this lesson. We'll take another quick break and we'll come back and take a look at the next lesson, which is involving another new feature, ICER. So we'll see you in a few minutes.